Bismillahirrahmanirrahim. Assalamu alaikum. Have a good day. So, this lecture is related to the production of energy levels in EPR under the influence of an applied magnetic field and the effect of that magnetic field is also recorded in terms of frequency that produces a signal, and in our previous lecture we have studied that the G factor is inversely proportional to applied magnetic field, and the G factor is also comparable to the value which is used in NMR spectroscopy. I forgot the name of that factor, that is chemical shift value. In NMR, the position of a signal is represented or located by chemical shift value, but in case of EPR spectrum, the value is determined in case of G value. So we shall also discuss about G value for free electrons and G values for some of biologically important paramagnetic species, and then we shall see the theory and position of a signal in EPR spectrum, and as usual the closing of the lecture will be at assignment. Energy levels in EPR based upon the spin of an electron and its associated magnetic moment. So far, a molecule with an unpaired electron in a magnetic field, the energy state of the electron can be defined as E is equal to G mu B B naught and ms. The ms of electron in an applied magnetic field will comprise of some of the electrons in antiparallel alignment and some of the electrons in parallel. That's why it is necessary to mention plus minus half rather than ms, because ms half of electrons will having plus half and half electrons will have minus ms. That's why the equation is summarized as plus minus half G mu B B naught. In this equation, G is proportionality factor, mu B is Bohr magneton, and B naught is applied magnetic field. Sometimes the mu B is also represented by beta. So don't be confused with the notation. And ms is electron spin quantum, that is plus or minus. From this relation, there are two important factors to note. First one, the two spin states have same energy when there is no applied magnetic field, as we discussed in previous lecture that there is no distance between these two energy states in the absence of an applied magnetic field. The energy distance difference between the two spin states increases linearly with the increasing of magnetic field. But one thing I would like to add, the distance between two spin states is directly proportional to applied magnetic field, but the value of G is inversely related to applied magnetic field. To find information regarding derivative of A over derivative of H is plotted against H to get the first derivative of curve. When the radiation is absorbed, a spectrum is produced similar to the left hand side. You can see the signal at left hand side is just like a hill, that is there is a base, and or we can say this is a tower signal. So the absorption maximum corresponding to the point where the spectrum passes through zero. This is the point that is used to determine the center of signal. From this tower type signal, the center point cannot be determined accurately. Then how can we find the center of this signal? This is a mathematical conversion of this signal into first derivative. What is first derivative? For a plot or a graph, usually we encounter two factors. One factor is presented as x-axis and the other dependent value is presented on y-axis. The first derivative is actually a plot of independent derivative, sorry, plot of independent variable that is on x-axis to the difference of two consecutive values of dependent variable. Means for y-axis you have values like 2, 10, 6, 16, 20, 25. But when you will take difference of first two values, means the first two values are 2 and 6, the difference of these two values will become 4. The next two values are 6 and 8, means the first value is 2, second value is 6, third value is 8. The difference of first two values is equal to 4. Then the difference of further two values means second and third, 6 and 8 will be equal to 2. So if you take difference of consecutive two values and you plot graph in this way, the shape of graph will be changed from a tower to the graph at the right hand side. And you can see the dotted line is bisecting the graph, the line which is the half of the portion is on positive side and half is in the negative side. So the first derivative will actually give you the center of point. So many readings or graphs are presented in this way. There is a very common and famous inorganic technique that is known as TGA, thermogravimetric analysis, which is usually used to find weight loss of any sample with respect to time and temperature. For that technique, the actual method to find weight loss with respect to time and temperature is also determined in first derivative. The TGA is explained or actually studied in form of DTGA. That's why it is sometimes easy or facile method to find the actual fact of the first derivative of any signal. Proportionality factor, that is represented by G. EPR spectrum is obtained by holding frequency of radiation constant, but the field strength is varied from a minimum to a maximum level. Absorption occurs when the field tunes the two spin states so that their energy difference is equal to the radiation of applied frequency. This is known as field for resonance. What is field for resonance? Sometimes I can give you a very simple example. Means one person is traveling on a vehicle and you want to give him something, and his vehicle is moving at certain speed. So then you can only transfer or pass anything to him when you are having the same speed as that of the speed of the vehicle of that person. So then we can see that is the field of resonance for both of two objects is same. A spectra can be obtained at a variety of frequencies. The field for resonance does not provide unique identification of compounds. G value of a free electron or proportionality factor G, however, can yield more useful information. G is equal to h nu over mu b into b naught. For a free electron, proportionality factor is 2.0023. For organic radical, the value is typically quite close to that of a free electron, with ranging from 1.99 to 2.01. For transition metal compounds, large variations can occur due to the spin-orbit coupling and zero field splitting, and result in values ranging from 1.4 to. This is a large image to represent the first derivative of the spectra recorded from EPR. G values for some biologically important paramagnetic compounds are presented in this slide. Flavin, semiquinine, ubiquinine, and ascorbate, etc. They have values 2.0030 to 2.0050. Nitro oxide spin labels and traps. In the next lecture, I shall explain to you what is labeling and trapping. Here just need to know their value is 2.0020 to 2.0090. For sulfur radicals SS or SH, the value is 2.02 to 2.06. For molybdenum in 5 oxidation state, in aldehyde oxidase enzyme, its value is 1.94, and copper, when it is in +2 oxidation state, the G value will be equal to 2.0 to 2.4, and when iron is in low spin state, mean when it is having inner orbital, means it uses inner subshell like D2sp3 hybridization, its value will be 1.4 to 3.01, and for high spin, when it is using sp3 d2 mode of hybridization, the value of the factor will be equal to 2.0 to 10. For high spin, the range of value is very large, so the change in value or variation is dependent on applied magnetic field, and the ligands are anions which are attached to a central metal atom, or we can say the value of G is dependent on applied magnetic field as well as crystal field. Further, there are some transition metal complexes. One is isocyanato molybdenum oxygen complex. Its value is 1.935. Then acetate, it has 1.968. For free methyl group is 2.0026. For anthracene cation, the value is 2.0028. For anthracene anion, the value is 2.0029, and for cupric acetate, the value is 2.1. Position of the signal in EPR spectroscopy. As mentioned earlier, that G value gives the position of signal. G is not a constant, and we have also studied that it is a unitless factor. It is a tensor quantity that changes with environment. For the same cation, like in previous slide, I discussed that iron +3 in high oxidation state has a value of G ranging from 2 to 10. So it means that it is not a constant, it is a tensor quantity that changes with the environment. Environment means the number of our Nature of ligands are anion attached to center metal atom. Many systems show G value close to the free electrons, but deviations are also very common. The deviation in the order of plus minus 0.05 may be mixing of low-lying electrons with ground state electrons. G value for 3D metal ions ranges from zero point 0.2 to 8. The, the variation in G value, the wide range is attributed to many reasons, that is LS coupling, crystal field splitting, and presence of inherent magnetic fields in the crystal. But LS coupling and oxidation state of ion makes the G value characteristics. When the operating frequency of instrument is not known precisely, then dpph is used as a standard. Or we can see the references which are used to calibrate the instrument is most common is dpph. It gives 5 extremely sharp peaks with an intensity ratio of 1 to 3 to 1 in a solid state, one sharp line, and its G value is 2.0036 into 1 minus delta H over H. Delta H is difference between standard and sample, and H is sample field. Which nuclei will interact? It is important to note that if a signal is split due to hyperfine interaction, the center of the signal which is used to determine the proportionality factor is the center of splitting factor. So for a doublet, the center would be half between the two signals, and for a triplet, the center would be the center of the middle line, measured as distance between the center of two signals. Now the term hyperfine interaction will be discussed in detail, maybe in the same lecture in some coming slides or in the coming lecture. So don't be confused that what is hyperfine interaction. So it has its complete description in coming study. So there are some selection rules for every spectroscopic techniques. The selection rules for the EPR are same as NMR. Every isotope has a ground state nucleus spin quantum number, and it has a value of n-2, where n is an integral quantity. Isotopes with even atomic numbers and even mass numbers have their spin quantum number I is equal to 0 and have no EPR spectra like carbon 12, silicon 28, and iron 56. Isotopes with odd atomic number and even mass number have n even, that include H2, that is deuterium, then boron 10 and nitrogen 14. Further, isotopes with odd mass number have n odd, like proton, carbon 13, and fluorine 19, and manganese 50. This is a signal that is a first derivative of absorption signal. Hyperfine interaction. In addition to applied magnetic field, unpaired electrons are also sensitive to their environment. Previously, we have studied about their sensitivity dependent on ligand, or we labeled that factor as crystal field effect. But there is an other mode of interaction of electron that is known as hyperfine interaction. Frequently, the nuclei of atom in a molecule or complex have a magnetic moment which produces a local magnetic field at the electron. The resulting interaction between the electron and the nuclei is called as hyperfine interaction. Means there are two modes of interaction of an electron. One is with the ligands and other species. That is known as crystal field effect. And in case of 3D elements, the crystal field effect is so strong that it quenches orbital angular momentum. But in case of lanthanoids, as I told you in second last lecture, that the contributing electrons are present, are seated more inside the cation, so the crystal field effect is not uh, effective to quench angular momentum. The other mode of interaction of electron is with the nuclei, and this is known as hyperfine interaction. Hyperfine interaction can be used to provide a great deal of information about the sample, including providing information about number and identity if nuclei in a complex, as well as their distance from the unpaired electron. Relationship for hyperfine coupling is presented in this slide. The interaction expands the previous equation to E is equal to G mu B B naught ms. The relation before plus sign is previously discussed. Now there is an additional factor that is known as A into ms into m1, where A is hyperfine coupling constant and m1 is nucleus spin quantum number for neighboring nucleus. You can see in this slide that previously the ms plus and ms minus, these two states have been produced due to the influence of applied magnetic field. Further, the energy of these two states is splitting or changing to a new energy level due to the influence of nuclei. So this is the interaction with a single nuclei having spin. This is a complete diagram which is showing that at zero field all of the electrons are at same energy level, so there is no splitting. But as soon as we apply a magnetic field, the red arrows up and down with negative and positive signs are showing that with the application of applied magnetic field, some of the electrons have been arranged parallel to applied magnetic field and some of the electrons have been arranged to applied magnetic field. But further, when these electrons interact with the neighboring nuclei, then each of the energy level is further split into two energy levels, that is represented by nu n, where nu is n is for the nuclear effect, and the red arrow that is in the center of this diagram is showing that field BZ, that is applied magnetic field. And further you can see the green arrows showing that these spin states have been further splitted or transformed into new energy states. So a single nuclei with a spin alpha will split each energy level into two as shown above, and then two transitions or absorptions can be observed. The energy difference between the two absorptions is equal to hyperfine coupling constant. The coupling pattern that are observed in EPR spectra are determined by same rule that applies to NMR. However, in EPR spectra, it is more common to see coupling to nuclei with spin greater than half. The number of lines which result from the coupling can be determined by the formula 2ni plus 1, where n is number of equivalent nuclei, I is spin. It is important to note that this formula only determines the number of lines in the spectra, not their relative intensities. For the determination of relative intensities of the signal, we shall discuss in coming lecture. So from this lecture you have to answer related to drawing a structure of dpph radical and explain the factor on which the value of G depends and what is field for. With this I would like to say thank you so much. Allah Hafiz. Will see you in the next lecture. Assalam.